Welcome students. So today we will start a new topic called sampling and quantization. So when you are studying digital communication, this is a very important topic to study because most of the signals that we come across in real world are not exactly digital in nature, and by that I mean that the signals are continuous functions of time and they have varying amplitudes at different points of time, and that's why we need sampling and quantization to convert those signals into digital domain. So let's proceed. So as I just said, the most common message sources that you come across in today's practical systems are audio and video, and they are analog in nature, and therefore we need to go through the following steps to properly use them for digital transmission. And these steps are sampling, quantization, and encoding. So sampling means that you are basically dividing the signals into uh, different values at different points of time, or in other words, you are just taking the amplitude of the signal at very closely spaced intervals of time, and then you are working with those values for further processing. So that is called sampling. And once you sample the signal, you take those sample values and then you represent that value by a digital symbol that is chosen from a finite set. So we will get into the details of this. So basically, what does this mean roughly? This means that when you sample a signal, let's say you are looking into the values of the signal at a particular points of time, and you have, let's say, uh, if it's a continuous time signal, then you can have different real numbers as the values of the signal. So you can have, let's say, 2.5 volts as the value or the amplitude of the signal at a particular instant of time, and then at the next sampling interval, or at the next time instant, you see 2.54. So maybe if you are choosing from a finite set of value, you have to round these decimal values to a particular value, and that is actually called quantization. And uh, and once you quantize the signals, then you map those quantized signals, uh, the quantized signal samples, into a certain string of digital symbols like ones and zeros that usually we have in digital communication system. So so this is what I meant. So this slide actually captures what I just said in a very nice way. So let's say you have this analog signal which is continuous in time, and you can see that the signal has continuous values throughout the time axis. So if you pass this signal through an arrangement where you have a switch here that is closing at every integer point of time. So let's say if your this capital T is, let's say, 1 second, okay, and you are basically choosing every integer multiple of capital T. So basically you are closing this switch at t equal to 1 second, t equal to 2 second, t equal to 3 second, and so on. You can choose capital T as even less than 1 second. You can choose 1 millisecond or 1 microsecond, whatever be the granularity. Let's say at every integer multiple of that capital T, if you are closing this switch like this, then then this will be sampling the continuous time signal. So you will get values like this. So let's say my switch was closed at certain point, so this gives me a value here. Then the switch was open for a while, then again it was closed, and this gives me another value here, and so on. So in that way you can see that you sample the continuous time signal across the time axis at regular intervals of time t, that is equal to an integer multiple of your sampling time, which is capital T. And you roughly get the same signal after the sampling, depending on how frequently you are closing this switch. You will get more or less a very close approximation of the original analog signal. And then this sampled signal is passed through a quantizer like this. Okay, so see, this quantizer, what it does is takes certain fixed set of values corresponding to the input sample signal. So what it basically means is that it approximates these levels, these sampled signals levels, to a finite set of values. So let's say I choose a 5-bit quantizer. Okay, so 5-bit quantizer means I have 2 to the power 5, which is equal to 32 levels. Okay, so if you now choose the entire range of the signals, which is, let's say, between 0 to 2.5 volts, 0 to 2.5 volts is divided into 32 levels. Okay, so basically 2.5 divided by 32, so whatever be that value, those are the finite increments of the signal. So now if I have a signal which is let's say, okay, let's do this math. So let's 2.5 divided by 32 is how much? Let's say this is 0, and let me work this out. So basically 2.5 divided by 32 will be 0.07 or 0.08. Okay, so let's say now I can choose only increments of 0.8. so I can choose 0 volt, I can choose 0.8 volts, I can choose 1.6 volts, and so on. So if I have a sampled value here, let's say 0.5, let's say here, somewhere here, let's say if I have 0.5, I can approximate it to 0.8. okay, if I have, let's say, 1 or 1.2, I can approximate it to either 0.8 or the next value that occurs, 1.6. So in that way I am kind of approximating the sample values to a set of finite values that is chosen by the quantizer here. So if it is a 5-bit quantizer, then you have less numbers to work with, you have only 32 levels. If you choose 6-bit quantizer, then you have 2 to the power 6 levels, which is 64, and in that way you can even have a better approximation of the sample signal. So if you see this quantized output versus this quantized output, you can closely and clearly see the difference, that the 6-bit quantizer is probably a more accurate representation of the original signal than the 5-bit quantizer. So this is the concept of sampling and quantization, and again, if you see here, it will be even more uh, clear to you. So if I have a signal like this, shown in red here, and if you choose only a 2-bit quantizer, so it can have 4 levels, and you can represent the signals with these 4 levels. So the highest point is denoted by, let's say, 1 1, then the next is 1 0 here, and then you have the next level 0 1, and then finally 0 0. Now if you represent the same signal with a 3-bit quantizer, then you can see that you always do a better job. So you have more levels to play with, and you can have a better approximation of the original signal here with a 3-bit quantizer. So this is the story that was also reflected in the previous slide when I showed you the 5-bit quantizer versus the 6-bit quantizer. So more number of bits you have for the quantizer, or in other words, more the resolution of the quantizer, the better it is. A better approximation of the signal can be obtained, and you can have less error associated with the quantization. So moving on, now if you want to theoretically represent this concept of sampling, then basically it is nothing but you have the input signal which you are trying to sample. Let's say, sorry about that. So let's say if you have the input signal here, which is your xt in this example, and then you want to sample this signal. So basically that means you are convolving this signal. So I am assuming that you have learned the concept of convolution in your digital signal processing class, and also signals and systems class. So if you are convolving this signal xt with another signal st, which happens to be an impulse train. So what does that mean? So basically, if you have an impulse function which has a very sharp spike at 0, and everywhere else it doesn't have a value, if you look with respect to time t. So this is your basically delta t, and then you can have different shifted version of this impulse. Okay, so let's say this is delta t minus ts. So this value occurs at t equal to ts, and then you can similarly have here at minus ts you can have delta t plus ts, and so on. So you if you increase this operation, or if you keep doing this throughout the positive t-axis and the negative t-axis, then you basically get impulse train, and that can be represented by this equation. So delta of t minus n ts, and n running from minus infinity to plus infinity, and if you sum them all, then you get an impulse train like this. And sampling is nothing but convolving the original analog signal with impulse train, which repeats every ts period of time, and that is actually your sampling period. So your ts is the sampling period, and then at the output of the convolution you will get the sampled signal. So if your signal looks like this, your xt looks like this, then after the convolution with the impulse train, your signal will follow the envelope of xt, but with regularly spaced impulse functions. So this will be your sample signal x of st, and that is what is happening here after the output of the sampler, or the convolution with the impulse train. And ts is the period of the impulse train, and this is also the sampling period. You can have the sampling frequency, which is 1 over ts, and and you can see it is very intuitive that higher the sampling rate, the more accurate the representation of mt by mst. So so sorry, this is this should be xt, but it doesn't matter as long as you get the concept right. So the input signal can be mt or xt or whatever, and then the sample signal is basically the convolution of that signal with an impulse train. And the more closely spaced the impulse train is, so the better is the sampled version representing the original version. So let's say if you have this signal, and if your impulse train is very widely spaced, then this probably is a less representative of the original signal than, let's say, if you have very closely spaced samples like this. So this represents the original signal in a better form. So now the question would arise that what is the minimum sampling rate for the sample version to exactly represent the original analog signal. So let's try to find out the answer to that question through this slide. So let's say you have your signal mt or xt, whatever, the notation doesn't matter as long as you get the concept right. So let's say you have your original signal in time domain. So this is basically time domain, and then the same signal in the frequency domain is represented by, let's say, this. So so basically if you take the Fourier transform of this signal here, then you get basically this frequency domain signal. And let's imagine that the frequency domain signal is band limited between plus w and minus w. So so that's the maximum range of frequencies that the signal contains. And now if you want to sample this time domain signal, so basically you are trying to convolve this time domain signal with this impulse train, which is spaced ts seconds apart. So that's your sampling time. Now if you represent this again, this impulse train into the frequency domain, then you will get the same impulse train. So basically the Fourier transform of a impulse in time domain is also an impulse in the frequency domain, but with different scale factors. Okay, so you can see that in the frequency domain the impulse train is also an impulse train which are fs frequency apart, and fs is 1 over ts. So and the amplitude in this case in the time domain was 1, and here in the frequency domain that amplitude becomes 1 over ts. So now if you sample this signal by convolving with this impulse train, then basically you get this this sampled signal mst, which is which looks like this. And then in the frequency domain, anything that is convolved in the time domain is basically a multiplication in the frequency domain which you know from signals and systems class. So so basically we are in frequency domain multiplying this particular signal with this impulse train, and this is basically repeating this signal, the frequency response of these signals after every fs frequency. So basically we have a copy of the original signal here, which is band limited between w and minus w, and then this copy repeats at fs. So this will be your this will be fs plus w, and this will be fs minus w, and then it repeats at again 2fs. So this boundary will be 2fs plus w, and this will be 2fs minus w, and so on. So basically the same signal repeats itself at an interval of fs, twice fs, thrice fs, and also in the negative direction at minus fs, minus 2fs, and so on. So so this is the sampled signal. Okay, so now let's say if I want to recover this signal, okay, so you want to reconstruct this signal from the sampled output. So in every digital communication system, when you sample a signal, you also need to recover that signal to generate the final analog output. Okay, when you are sending the signal from the transmitter side, you are sampling it, you are quantizing it, and then you are encoding it, and then you are sending it over the channel, and then when you receive it, you just do the opposites. So you decode the signal, you dequantize, and then you reconstruct the samples to get the original signal. So now if you want to reconstruct the original signal, so this is the frequency response of the sampled signal, which contains the original signal here, and also the copies of the signals repeated every fs frequency. Okay, so to recover the original signal, which looks like this, I just want to have a low pass filter with gain 1 that just captures the original signal, and I want to just remove these parts. So I don't want this one, and all, and this one, and this one. So I just want this part. So what I will do is I will pass the entire sampled signal through a low pass filter, and in frequency domain that low pass filter will just capture this part of the signal, which is the original signal. Okay, so now coming to the point, how frequently you can do the sampling to represent the original signal, or to reconstruct the original signal, can be found from this figure itself. So let's say if you focus into this part of the diagram, okay, or maybe let me redraw this freshly. Okay, so let's say if I have let's say this was my original signal. Okay, so this is 0, and this is w, and this is minus w. Okay, so now let's imagine that this has been sampled, and I have another copy here, okay, which is at fs, and then I have also repeating copies this in this direction and in this direction as well. So I'm not drawing them, just for the sake of clarity I'm just drawing one copy that is repeated. Okay, so now if you see that since the signals is band limited between W and minus W. So now consider this repeated copy, which is now centered at frequency Fs, and this will be then Fs plus W. So this extreme, and this extreme will be Fs minus W. Okay, so now as you saw in the previous slide, we were trying to put a low pass filter and pass the signal through it, and let's say this is the boundary of my low pass filter, and I want to pass this signal, the original signal, which is this one, through the low pass filter, and I don't want any other copies of the sampled signal to go through the low pass filter. So let's say if this Fs minus W is exactly falling here, let's say instead of falling here, if it falls here at this point, then also I can design a low pass filter which sharply cuts through this. Okay, and you can still recover the signal. Okay, so I'm sorry. So if your low pass filter sharply cuts through this point, you can still recover the signal. So at most the repeated copy can just fall on this point. Okay, so the beginning of the repeated copy can be from this point, but it cannot be here. The repeated copy cannot start from here. Okay, in that case the low pass filter will capture this part of the repeated copy. So this phenomenon is called aliasing. Okay, aliasing, and you don't want this to happen. So to ensure that this doesn't happen, your W and Fs minus W can at most be equal. So Fs minus W can, if that is equal, then both of the original signal and the copy signal just fall exactly touching each other. Okay, and if your Fs minus W is slightly greater than W, then you have a space. Okay, so that your low pass filter can completely cut out the original signal, and you don't have any just a second, sorry. So so your original signal, if your Fs minus W is greater than W, then your original signal has some space between the repeated copy, and your low pass filter can exactly capture your original signal and filter it out without any aliasing. So I can write that Fs minus W can be either greater than or equal to W, so that you can properly capture your original signal and filter it out, and hence reconstruct the original signal from the sampled value. So this, in other words, says that your Fs, or the sampling frequency, has to be greater than equal to twice of W. Okay, so this is basically called Nyquist sampling theorem. Okay, so this was proposed by Nyquist, and this is basically the requirement for the sampling, like how much you want to how much spacing you want to have between your sample time. Okay, so basically your fs, or the sampling frequency, this one should be greater than equal to twice of w. So if a signal is band limited between minus w and w, then your sampling frequency has to be greater than or equal to twice of w, and therefore your sampling time ts, which is 1 over fs, has to be less than or equal to 1 over twice of w. So this is the requirement. Okay, as long as your sampling time is less than equal to 1 over twice w, you are good. Okay, so basically we asked ourselves the question here in this slide, that how much should be the minimum spacing or the minimum sampling rate so that the sampled version exactly represent the original signal. And the answer is, after all this analysis, is your sampling rate should be separated by time instants that are at most 1 over 2w, and in other words your sampling frequency fs has to be greater than or equal to 2w. So this is known as the Nyquist criteria or Nyquist sampling theorem, and if you follow this, then you can successfully recover the signal from its samples. So I'll stop here in this video, and then we will continue in the next video with signal space analysis.